Okay, so we're recording. Now we're looking at section 1.7. We're going to talk about linear independence of vectors. So there's a formal definition in section 1.7, this definition here, that says, hold on here, sorry. Yeah, what this says is, hold on, let me get my email off here. I don't want any distractions here. Okay, I'm back. Wait, where are my students? Here we are. Okay, so if you have a set of vectors in a space, in n-dimensional vector space, the set of vectors is linearly independent if the only solution to this, well, you see the highlighted vector equation says take a linear combination of all the vectors take a linear combination of the set of vectors in this n-dimensional space. Set that linear combination equal to the zero vector. If the only solution to x1, x2, x3 up to xp, if the only solution to the variables is the trivial solution, and the trivial solution means that x1, x2, x3 up to xp, that all those variables equal 0. If that's the only solution, the trivial solution, then we say the set of vectors is linearly independent. However, if there's another solution besides a trivial solution, then we say the set of vectors is linearly dependent. Okay, and there's a linear dependence relationship among the vectors. Now, this is best seen by looking at an example. So I'm going to go right away to a couple of examples. Okay, let's look at this one here. Okay, let me give you a moment to copy that example down. Okay, so we have here two vectors, a vector v1, which is 3, 1, has coordinates 3, 1, and vector v2, which has coordinates or components 6, 2. Are the vectors linearly independent? What do you think? Do you think the vectors are linearly independent? Okay, so the different people have different thoughts. Is vector 2 at all related to vector 1? Okay, how is that, Mikhail? How is vector 2 related to vector 1? How is vector 2 related to vector 1? That's right. The second vector is twice the first vector. That means there's a dependence relationship between these two vectors. Twice the first vector is equal to the second vector. So these two vectors, yes, they're two vectors, but they are linearly independent. They are not linearly independent. So, you know, if we were to sort of be more formal here, I mean, this is what we said. The second vector is twice the first vector. Okay. But another way to think about it, if we're thinking about the definition in the book, is if I were to look at this vector equation, which says take a linear combination of the vectors, set it equal to the 0 vector, it turns out that x1 and x2 x1 is -2, x2 is 1. That's a non-trivial solution. A trivial solution would be x1 equals 0 and x2 equals 0. And let me just see here one moment. It's called a trivial solution because that's true for any collection of vectors. You know, 0 times v1 plus 0 times v2 will equal the 0 vector. That's trivial. But we have a non-trivial solution as well. And because we have a non-trivial solution, that implies that the set of vectors, v1 and v2, are linearly dependent. Okay. Are there any questions on that? All right. Give me a thumbs up if you're good with this so far. Give me a thumbs up. Okay, Yasin's comfortable, Mikhail is comfortable, Cameron and Jonathan and Marcella are comfortable. Wonderful. Bellen's comfortable. Okay. All right. Well, let's look at another example. Then let's look at another example. Let's take an example where we have three vectors, v1, v2, and v3, all in R3. And I want to know if those vectors are linearly independent. Let me give you a moment to copy the example down. So we want to see if the three vectors are linearly independent. And the way I like to think of this is, well, I think, well, if the vectors were linearly dependent, then that means that one vector is related to the other two vectors, right? So v1 would be related somehow to the vectors v2 and v3, for instance. That would imply linear dependence. Okay. I'm trying to see if the vectors are linearly independent. So what we need to do is we use the definition in the book to set this up. Here's the definition in the book. Again, we go to that vector equation. Does this vector equation, where we take a linear combination of the vectors and set that linear combination equal to the 0 vector, does that vector equation have only the trivial solution? That's what we have to check for. So we're going to solve this vector equation, and we have to write the vector equation as a system of linear equations. hold on here, making sure which I've done here. Let me give you a moment to catch up. Here's the augmented matrix. Please let me know if you have any questions. Okay, so here's our augmented matrix here. And we're going to do row operations on that augmented matrix to try to get it in reduced echelon form, because we're trying to solve for x1, x2, and x3. So now I'll go to the next page. It can be shown that I would show the row operations, but in the interest of time, it can be shown that this augmented matrix is row equivalent to this augmented matrix in reduced echelon form. And based on the fact that we have zeros here in the bottom row, okay, and again, when they say zeros in the bottom row, that just means in this case 0x1 plus 0x2 plus 0x3 equals 0. You see, that equation is not really informative, right? That equation's not informative. I mean, we have a consistent solution, but the information in terms of the solution, the basic variables, comes from the first two equations. The third equation is really non-informative. So we have one free variable and two basic variables. We're going to let x3 equals free. X3 is the free variable, and x1 and x2 are as you see them. So we ended up with a non-trivial solution. This means then that the set of vectors has to be linearly dependent. Linearly dependent. Because we can get, well, there's an infinite number of solutions, right? An infinite number of solutions to the vector equation. x1 times v1 plus x2 times v3, sorry, let me state it again. x1 times v1 plus x2 times v2 plus x3 times v3 equals the zero vector. There's an infinite number of solutions for x1, x2, and x3 beyond the non-trivial solution. Now, I like to make this a little more concrete. So, like, for example, if x3 were equal to 5, if we just set x3 equal to 5, then x1 would have to be 10 because x1 is 2 times x3, and x2 would have to be negative 5 because x2 is negative x3. So that means then that 10 times the vector v1 minus 5 times the vector v2 plus 5 times vector 3 equals a 0 vector. But you could also think of this, if we were to solve this vector equation for v1, vector v1 would be 5 halves v2 minus 5 tenths v3. Or v1 is 1 half v2 minus 1 half v3. So you see, v1, the vector v1 is related to the vectors v2 and v3 by that equation. There is a relationship between the vectors v1, v2, and v3. So you see, anytime you have a non-trivial solution, you can relate one vector in the set of vectors to the other vectors in the set of vectors. You can relate one vector in the set to the other vectors in the set by a vector equation, such as like I did here. And that helps me feel very comfortable about linear dependence. This equation here, this vector equation, v1 equals 5 halves v2 minus 5 tenths v3, shows you how v1 is related to v2 and v3. Okay. Are there any questions on that? Okay, let me ask you a question then. If you're good with this. Let me ask you a question. Let's say you had this set of vectors, E1, E2, and E3. Is that set of vectors linearly independent? So E1 is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. That's like I, J, and K. That set of vectors, okay, what do you think? Mikhail and Bellin think that set of vectors is linearly independent. Can one vector, so yeah, they are. So, you know, sometimes to help you feel comfortable with ideas, it helps to think of like a nice example, a nice, easy example. The vector E3, for instance, the vector E3 cannot be written as any linear combination of E1 and E2, right? The vector E3 cannot be equal to any linear combination of E1 and E2. E3 is not related to E1 and E2. They are linearly independent vectors. So does that help you sort of get a feel for linear independence and linear dependence? Are we comfortable with that? Was this a nice, helpful example here? Good, good, excellent, Jonathan, excellent. Okay, well, let's fit in one more here. Let's fit in one more. Okay, let's fit in one more. Okay, let me give you a moment to copy this example down. Okay, so we want to find value or values of H for which these three vectors are linearly dependent. Linearly dependent. Okay, so how are we going to do this? Well, let's remember the vector equation for linear dependence or independence. The vector equation would be x1 times v1 plus x2 times v2 plus x3 times v3. And what do we set that equal to? That's right. Good. Good, Balin. Good, Michaela. We set it equal to the zero vector. So that's what we're going to do with these three vectors. We're going to set up this vector equation. So let me go to the next page here. Now what I've done, you have a thing that can magnify the screen. But I like how the book wrote out this. So I'm going to go with this. To study the linear dependence, okay, to study the hold on here. To study the linearly dependence of the three vectors, row reduce this augmented matrix here. That augmented matrix is just notation for this. Whoops. Right? That can be written in augmented form. Well, let me just put it over here, in augmented form. Hold on. I'm going too fast here. I'm making mistakes. This isn't right. Yeah. So this vector equation here reduces to this augmented matrix. And this is how we denote the augmented matrix symbolically, right? So we're going to do row operations to get the augmented matrix down to this form here in the third matrix. What form is the third matrix in? This augmented matrix here. What form is it in? Is it in reduced echelon form or echelon form? That's right, echelon form. That's right, Nikhil. That's right, Jonathan. And that's because in order to determine consistency, we only need to get the system, the augmented matrix in echelon form. Okay. So if we look at that, well, take a moment. So they didn't show, they don't, I mean, there were row operations that were done. Obviously, they used the 1 here as a pivot to produce zeros where the -1 and the 4 are. All right. And then they used the -2 as a pivot to produce a 0 where the -5 is. They multiplied the second row by 5 halves, -5 halves. Right. And so, one moment here. Yeah. In other words, this, I don't think it'll hurt to maybe point this out. But this H-6, that comes from taking -5 halves times 4 and adding it to H plus 4. This is -10 plus H plus 4. So that's -6 plus H. That's how they get that entry there. So we look at the last row. We study the last row. Okay. And we want a non-trivial solution. Non-trivial solution. Well, if the last row here, and I'm looking here, if the last row read 0, 0, 0, 0, okay, the last row, what would that imply about, what would that imply? In other words, it would read 0x1 plus 0x2 plus 0x3 equals 0. What would that imply about x3 if we had a row of zeros here at the bottom? Why infinite solution, Bellin? You're right, because x3 would be any number. It'd have to be a free variable. That's right. And then you would solve for x1 and x2. So that would only happen if h minus 6 were equal to 0. Right? And so the vectors would be linearly dependent only if h were equal to 6. Because if h equals 6, we would get a row of zeros at the bottom of our echelon form matrix, and that would imply that x3 is a free variable, and so non-trivial solution to the vector equation here. So you see, this little exercise is designed to force you to understand the concept behind what linear dependence means. Okay, are there any questions on that? Are there any questions at all? Okay, very good. Let me stop the recording. So these are some nice examples for section 1.7 that we did today. And of course, the book has some good examples as well. Let me go ahead here and stop the recording. Excellent.